So for this chapter, there's really one problem that I want to discuss with you that's a bit challenging. And that is that I've asked you to calculate the equations of motion using Poisson brackets. So in the Hamiltonian formulation, and I want you to verify that the result that you get agrees with what you got using the Lagrangian density. So first of all, what should the equation of motion be in the Hamiltonian formulation? Well, you'll just have phi dot of x and t will be equal to the Poisson bracket of phi of x and t, commutator with the Hamiltonian. And then you will also have pi dot of x and t is equal to the Poisson bracket of pi of x and t with the Hamiltonian. And remember, the basic Poisson bracket that you should use is that the Poisson bracket of phi of x and t with pi of y and t is just the Dirac delta, delta x minus y. Good. Okay, so just a few things. Well, you know what the Lagrangian is for the free scalar field. We've got the kinetic term, a half d mu phi. And then we've got a second potential term, minus 1/2 m squared phi squared. The Hamiltonian density is given by pi phi dot minus the Lagrangian. So you should go ahead and calculate what is pi. So remember that pi is equal to dl d phi dot, and you should find that this is just phi dot. So that's the first thing to check. And then if you use this expression for pi inside the formula for the Hamiltonian density, and you rewrite everything from pi dots to phi's, the answer that you should find is 1/2 pi squared plus 1/2 gradient of phi dotted into the gradient of phi plus 1/2 m squared phi squared. So that'll be the Hamiltonian density, and then the Hamiltonian is nothing but the integral d3x of the Hamiltonian density. So it is the Hamiltonian and not the Hamiltonian density. It's the Hamiltonian that appears inside the equations of motion, okay? Then what should you do? So this first equation over here should tell you that phi dot is equal to pi, and then you should plug it into the second equation. And this is from this second equation, you should now get something that agrees with what you got from the Euler-Lagrange equations. One point when you're doing this calculation is that you're going to need to calculate the Poisson bracket between a derivative of the field, let's say derivative with respect to x by x. I just want to be explicit about what that derivative is. And perhaps you've got a pi of y comma t, something like that. Okay, so that's what you're going to have to calculate. Now, remember that the Poisson bracket involves functional derivatives. Okay, so what this Poisson bracket is equal to, it is actually the derivative of a Poisson bracket that you know. So if you've got the Poisson bracket of the derivative of a field with something, you can take the derivative of the Poisson bracket with that field. And now, recalling that the Poisson bracket involves functional derivatives, what assumption are we making? We are making an assumption. The assumption that we're making is that if we were to calculate the functional derivative of some other coordinate, x, y, let's call it z, onto dx on phi of x comma t, we are claiming that these two derivatives commute. So that's the basic thing that we are claiming. when we pull the derivative out of the Poisson bracket. So why should these two derivatives commute? Well, let's think about what these two different derivatives are doing. So nabla, this derivative, is calculating how the value of the function changes when we change x. So it's comparing the function at two different x values, okay? So it's really messing around with the x argument of the function. What is the functional derivative doing? The functional derivative is calculating the change when you change the entire function, okay? So these two derivatives actually act on two different spaces. Nabla acts on the space of functions, whereas the functional derivative is acting on the space of functionals. And because these two derivatives act on different spaces, in general, you would expect them to commute. So this is the assumption that we're making, that these two derivatives commute, and they do. And with that assumption, you can easily calculate the Poisson bracket of the derivative of the field as just the derivative of the Poisson bracket involving the field. Good. Okay, guys, good luck. I hope that you managed to tackle these exercises, and let's get going with the next chapter.